The next periodic trend we're going to talk about is electronegativity. Now, for an organic chemist, electronegativity is actually very valuable. Okay, now something that we want to focus on and kind of explain what electronegativity is and how it's different from things like ionization energy, electron affinity. Okay, so down here, I've already written all these elements out. And down here on the bottom, I'm going to explain what this is. So for ionization energy, what we're talking about is that an element absorbs some energy, and what happens is that your element loses an electron. All right, so the element gains a positive charge and electrons lost. For electron affinity, you have an element and it gains that electron to become E minus. All right? For electronegativity, we don't have an actual electronegativity. Can't talk while I spell complex things. Okay. Electronegativity, what this is that you don't have a formal transfer of electrons. But what you do have is the want of that nucleus to pull electrons towards itself. Okay? There has to be an impetus on why things want to pull electrons towards themselves. So it's the pull in bonds, and this is important, in bonds of electrons towards certain atoms. That's towards, and I've written off the screen. Sorry about that. All right, so it's the pull of the atoms towards specific atoms. Now, if you think about the atoms that are on the periodic table, they all want to be like the noble gases. Noble gases over here are in purple, because purple is the royal color, right? So I've got neon, argon, and krypton listed here. Not included are things like helium and xenon and radon. Those noble gases, they do exist. They exhibit similar properties to what we're talking about, but I'm just talking about these particular rows, okay? So I've got neon, argon, and krypton. Each one of those is special because they've got that full outer shell, the full valence of electrons. By having that full valence, they don't want to gain any more electrons, right? So they don't like bonding to other things. Bonding requires giving up electrons or sharing electrons with something else. Why would they do that? They're full, right? Now, if you look at fluorine, chlorine, and bromine, each one of those is one electron away from each one of these noble gases. Remember the electron affinity. It was a huge number, like 300 joules worth of energy. That's the amount of energy that each one of these is going to grab when it grabs one of those electrons. Okay, so all of these want an electron. When they get that electron, they're going to look like the noble gases, right? Okay, so each one of them is grabbing electrons. They're going to look like noble gases. The same over here with oxygen, sulfur, and selenium. Okay, these things want to grab electrons to pull them towards themselves in order to be more like the noble gases. As I move this way on the periodic table, as I get to more metallic character, things that are metals don't mind giving up electrons. If you think about the famous molecule, nickel, okay, this is what my daughter was telling me the other night at the dinner table. Dad, pass me the nickel. And I was like, what are you talking about? She's not nickel, sodium chloride. Salt, okay, she's clever, and she likes to show that off. So here's sodium chloride. If you look at the ionic form, sodium is plus and chlorine is minus. The reason that being is that the chlorine is more electronegative and it's got a greater electron affinity. So it likes to pull that electron away from sodium to become more stable. Sodium, on the other hand, by losing that electron, gains the stability of that inner valence that's full. Okay? So both of these like giving up their electrons. There's a lot of energy to be gained there. If you actually look at this, if you take an evacuated flask and drop in sodium with chlorine, you'll see this very fiery type of reaction. And that's all that energy that's being released. from just metallic sodium and chlorine gas reacting. Okay, so the metals on this side, they like to give up electrons. So their electronegativity is not going to be a large value. All right? As a matter of fact, if you look at lithium, lithium has a value of 1. All right? So there's lithium with a 1. And as I move up the periodic table to beryllium, boron, carbon, nitrogen, oxygen, and fluorine, okay, all of those values represent an increase in the electronegativity. Neon obviously doesn't have any because it doesn't want any more electrons. So the king of electronegative atoms is fluorine right there. So I'll draw a little crown on it here, okay? Here's a little crown. There you go. Congratulations, fluorine. It's the Burger King right there. So fluorine is the king of electronegative elements, okay? If I move down the table, what do you think is going to happen? I'm now going from that smaller 2 shell to a larger 3 shell. So what do you think is going to happen as far as attractiveness of the elements to that element? What do you think is going to happen in a shielding standpoint? As I pull the electrons towards the nucleus of sodium, I've got that full second shell repelling electrons. So this guy is going to have a greater shielding coefficient for its outer shell than lithium does. Okay, so I should see an impact on that as far as the electronegativity goes. It's not giant, because I've only got 1 electron in that outer shell. And for sodium, it's 0.9. Okay, so not a giant value. For magnesium, it's 1.2. For aluminum, which is considered a metal, it has the same electronegativity value as beryllium. We move to silicon, and I go to 1.8. For phosphorus, I jump over to 2.1. Sulfur is 2.5, and chlorine is 2.9, no, 3.0. Okay. On the next row, I look at bromine, I get a 2.8. Selenium, my value is 2.4. Arsenic is 2.0, germanium 1.8. Gallium is 1.6. And calcium and potassium are 1 and 0.8. Okay? So those are all the values. Those are electronegative values. And as you can see, as I move down the periodic table, because of that shielding increase, I'm going to see a decrease in electronegativity. So electronegativity decrease. As I move down the periodic table. And as I move towards fluorine, right, I see a gradual increase in electronegativity going across the periodic table. So moving this direction, now you're going to see an eneg increase. Okay. The important things about electronegativity is that all of these are associated with bonds in some case. Now, we haven't really talked much about bonds. The 3 types of bonds that there are. There's metallic bonds. I mentioned them. Now I never get to mention them again. Metallic bonds are between 2 metals. We have ionic bonds, like sodium chloride, between a metal and a nonmetal. And we also have covalent bonds between 2 nonmetals. Right? Electronegativity has a huge play in each one of these. And for all molecules, the electronegativity is going to determine whether something's polar or something that's nonpolar. All right? So let me explain why electronegativity is important here. So I'm going to pause and then erase. All right. So for electronegativity, if I've got a bond, say sodium chloride, I'll use this again. For sodium and chlorine, there's a big difference between the 2 values. Chlorine has a 3.0 and sodium has a 0.9. What this means is that there's such a large difference here. The difference here is 2.1. That means that the electron is really spending a lot of time over here in the chlorine and not so much time over on the sodium. And this is what we expect. This is what we see. The chlorine actually steals the electron in these ionic bonds. Okay? So this is telltale of an ionic bond. And the ionic bond is a metal-non-metal interaction. And for the most part, in these metal-non-metal interactions, we see a difference here of about 1.5 to 2.0, somewhere in there. And that is not a 5. 1.5 to 2.0, okay? And I've forgotten an element here. I'm going to throw this in here. Let me erase krypton. I'll put this over here. Hydrogen, it's in a column all by itself, all right? But its electronegativity is actually important as well, all right? So ionic bonds, I have large electronegativity differences between the two, okay? So anything that's greater than, say, 2.0, you're going to have a metallic bond. So if I have, say, carbon and lithiums, I've got a 1.5 difference. And there's some people who argue that it's a metallic or an ionic bond, and some people argue it's a covalent bond. You get into these types of discussions, and it's a lot of hair splitting, okay? But for the most part, because carbon's a non-metal, lithium is a metal, I like to call it an ionic bond just for consistency's sake, all right? So that's an ionic bond. Now I want to talk about covalent bonds, okay? And I'm going to talk about carbon-carbon, okay? Now look at carbon and carbon, and my values are 2.5 and 2.5. Well, guess what? They're the same. So what do you think about the pole of electrons on both of those nuclei? They're both the same. So the electron distribution in this bond is going to be pretty much uniform between the two. And this goes for anything that's going to have a similar value electronegativity. So carbon and carbon, okay? But guess what? Look at sulfur over here is 2.5. So carbon-sulfur bond is going to be very similar in electron distribution because their electronegativities are the same. So if I have a difference of the two that's less than 0.5, I have something that's a non-polar covalent bond. Right? If you think about something like gasoline, you notice that gasoline, when spilled, floats on top of water or oil. You know, you look at those nice rainbow colors after any rainstorm, that's oil sitting on top of water. Because it's nothing but carbon-carbon and carbon-hydrogen bonds, it's non-polar. Okay? If I look at carbon-hydrogen is 2.5 and 2.1. The value is less than 0.5 difference, which means that it's going to be a non-polar bond. Now let's look at something else. If I've got oxygen and hydrogen, the value here is 2.1, oxygen is 3.5, my difference here is 1.4. I'm not to the point where I get into ionic character, but this is a really polar covalent bond. And when you get fluorine involved with things, fluorine likes to make covalent bonds that are really, really polar. I mean, close to ionic as far as their polarity goes. Okay? So these are the three important things that you need to know about these characters. OH, if you notice, is part of a very polar molecule you're all familiar with, water. Right? HOH. And it's got these very special properties that are incredible, allow life to exist, and a lot of water does is, sort of the opposite of what we expect it to do. But water itself, because it's got these OH bonds, okay, makes it very polar. Now, none of you should be doing this yet because you're all freshmen in college. But if you have a CH2 here and a CH3, that's ethanol. Also, the alcohol that you find in booze. It dissolves very easily in water, even though it's got this nonpolar component. All right? If I change this over, okay, and I put more carbons on here, to butanol, butanol has different characteristics, and it's not nearly as soluble in water as ethanol is, because it's got more of this nonpolar component. Okay? That's why electronegativity is important. And I want you to recognize what the trends are and be able to recognize when you have an ionic, a covalent, or a nonpolar covalent bond.